Hello. Hello.
Hello.
Brendan got his PhD from the University of Hawaii and then came here as a postdoc across the street in GPS on a JCPA fellowship, right? And then moved to UT Austin, another prize fellowship, and then got a Hubble fellowship before being part of the faculty there in 2018. And he stayed in UT Austin until a few months ago, and he had the good idea of moving back to California. So he's been in Santa Barbara for the past few months, starting a new gig there, and we are all very lucky to have him back here working with us as part of the K community and as a collaborator. So Brennan is an expert in the direct imaging and spectroscopy of planets, exoplanets, using a slew of facilities from Keck to a lot of facilities in Texas when he was at UT Austin, but also now focusing his attention to the Gaia mission, which I'm sure we'll hear about today. So I'm really excited to welcome Brennan here and to hear about his work on the formation of planetary systems from the outside in. I'm more of an inside out person, but let's hear it from you. So let's welcome Brennan.
Okay. Thanks a lot. I appreciate it. I love being back here. It's actually the first time I've been back, I think, on campus since 2015 or so. So it's really nice seeing everybody, reconnecting, and it's been a busy day of fun talks. So I want to start off, the theme of the talk is about planet formation and evolution, and the story we can begin to tell about planets from their birth to their very dynamically rich outcomes at older ages. And I'm going to focus on giant planets because those are the easiest ones to detect. They're the ones we can assemble this narrative with the greatest precision. And I want to start with just looking at this beautiful protoplanetary disk, HD 169142. It's one of my favorites because it's one of the largest disks that's been imaged with or observed with ALMA. This is a sub-millimeter wavelength, so we're seeing particles here that are kind of at that scale, millimeter-sized particles. So this is dust and small grains. You can see asymmetries, you can see structure, everything here, modulo kind of things in the noise level. All of the things that stand out as being real are indeed real. So filaments here, wakes, this decrease in flux here for this inner ring. To me, when you look at the scale bar here of 10 AU, it really reminds me that when we think about planetary systems and planet formation, so much of the discourse focused at spatial scales that are hugely discrepant with the scale of protoplanetary disks. And there are reasons we do that. The disk surface densities are dramatically higher. It's where most of the action takes place. But there certainly is interesting stuff happening. And so I think that we're in the early stages. We are in the early stages as a community, as a species, in our understanding of exoplanets and their formation and how they evolve. But we can begin to say something about the contours of this narrative. And I think just to appreciate where we are in time, it's helpful to look back. There are so many examples of this, early papers. We could go back to Greek philosophers. In this case, I wanted to just highlight a couple words from a report of a meeting in 1976 that took place at Lick Observatory in Santa Cruz, or near Santa Cruz. And it was titled The First Workshop on Extrasolar Planetary Detection. So of course, at the time, no planets had been discovered, but it was an effort from a small group in the community to begin to delineate and articulate the different techniques and the different scales of precision that are needed. So with direct imaging, astrometry, and radial velocities. It was chaired by Jesse Greenstein, who was a faculty member here and chair of the department, and from what I read, launched the graduate program in astronomy here at Caltech. So I'll just read a couple remarks here. So this is on the first day. The meeting began with remarks by Jesse Greenstein, workshop chairman. Greenstein first outlined the principal motivation behind the convening of this workshop, namely the question of whether planets are ubiquitous, a ubiquitous phenomenon in nature. He pointed out that although attempts had been made to estimate the frequency of planetary mass objects, and remember, none had been detected so far, so people had tried to estimate this frequency by observing population densities of low mass stars. Such extrapolations are not necessarily valid. So of course, we try to do the same things now. We extrapolate to low masses or wide separations. But in this talk here, I'll try to focus on what we've measured so far. But to me, it was amusing being able to, or attempting to try to extrapolate from the occurrence rates of low mass stars in the IMF all the way down to planets. You know, when I read it, I did not see much on the transit approach. Yeah. The minutes are available. So if for anyone curious, I found this through an obituary of George Herbig, written by Bo Reiperth. And so it's buried in a footnote. There's a link here to the minutes here. Okay, so fast forward 2 decades later, the discovery of 51 Pegasi b, the first giant planet orbiting a star, single sun-like star, 1995. And the workshop to commemorate this effort, we just reached the 30th anniversary of the discovery last month. So there was a conference at l'Observatoire de Haute-Provence in southern France last month. I attended, and here's Michel Mayor, who's the Nobel laureate and discoverer of this first planet, reflecting on this era. Okay, and of course now we're at over 6,000 planets that have been discovered. So I'll try to synthesize a little bit about this for a subpopulation. One of the most remarkable results in my mind that has emerged over the past decade is this remarkable diversity of protoplanetary disks. So there's a bit of a chicken and egg problem here of if planets form, they shape the disk, and there's material there that can also form planets. But these are really sort of the representatives or representation of the initial conditions of planet formation. So on the left here, this is just a gallery that shows some of the observations in scattered light. And here you're seeing submicron-sized grains, sort of in the atmospheres, the surfaces of these disks. In many cases, you can see sort of dark lanes where the material is obscured. You can see flaring and warps and interesting, clearly dynamically interesting processes occurring. And on the right, these are observations, just a small subset of the tally must be now in the about 100 or so spatially resolved disks with substructure. They're all sort of unique snowflakes. So here you're seeing the grains, you're seeing the dust, and you're seeing the material that's being carved out presumably by planets. There have only been a couple places now where planets have been directly linked to these substructures. But it's assumed that planets are the things that are causing many of these divots and especially these gapped rings. Okay, now this diversity is imprinted in the population of planets that we see. When we take a step back and look at the correlations among protoplanetary disks, the first obvious correlation that was known even in the era of SMA, but that was much more, was refined to a greater degree with ALMA, is this correlation with stellar host mass. So as you crank up the mass of the star, it's basically a proxy for the mass of the disk. And so we see higher protoplanetary disk masses. And there's all these nuances and caveats about how masses are measured, but it's clear that there's more submillimeter flux emerging from these disks. For a given mass, the diversity is also quite high. So something like 2 orders of magnitude, sometimes 3, for a given host mass. There's also a large dynamic range given age. So if you look at, these are survival functions. So it's sort of if you look at a star-forming region and find all the stars and measure their disk masses, this is like a cumulative distribution function, except 1 minus that. So we start at 1 and go down to 0 here. And it's organized as a function of age here. So these are younger systems here with more mass and older systems down here. But irrespective of which region you target, the dynamic range remains at the scale of about 100 in terms of disk masses, and it's preserved over time. And the disk sizes, at least the dust disks, are also very large. There's a large spread in dust disks from about 10 AU out to several hundred AU, several orders of magnitude in size. Now, these planetary systems inherit this diversity of their protoplanetary disks. And of course, I hope you're all familiar with the incompleteness of this map of mass versus separation. We're simply not sensitive at this point to this region in the bottom right. But where we are sensitive, the regions to which we are sensitive, we find planets. And there are different reasons why these various techniques, the transit method, the radial velocity approach, and direct imaging, probe different regions, why they're sensitive to different areas of this map. Transits quickly decay. So the geometric transit probability scales as 1 over the distance. And so the probability quickly decays. So we start finding fewer at about an AU, given the baselines of missions like TESS and Kepler in particular. For a given radial velocity semi-amplitude, the sensitivity to planet mass scales as 1 over the square root of r. So if you increase your distance by a factor of 4, you decrease your semi-amplitude. And so your sensitivity gets worse to a given planet mass as you march outward. And for direct imaging, the bolometric luminosity, which is really what we're sensitive to, the flux that emerges from the object, it scales as planet mass to the 2.5. So it's heavily sensitive to the planet mass. And it's also sensitive to age, as something like t to the minus 1. So that means that for direct imaging, we are more sensitive to massive objects at younger ages. But we also cover a region of these disks than the close-in region within 1 AU or within a few AU for RVs. Now, we're not completely sensitive to the giant planet regime, but I'm going to attempt to stitch some of this together here and just remind you why they dominate the mass budget. So, they represent something like 0.1% of the mass of any planetary system, but so they're really sort of the crumbs, the leftovers of the star formation process. And among those crumbs, the giant planets make up the most mass. So for Jupiter and Saturn in the solar system, it's something like 90%. They also make up the bulk of the rotational and orbital angular momentum. So if you add all that up in the solar system, it's at the scale of something like 90% for Jupiter and Saturn. They dominate the dynamics of planetary systems. So if they take on any sort of eccentricity, they'll clear out annuli within which smaller planets won't be able to reside. And that's relevant for giant planets that might be located near their habitable zones. And of course, they're the most detectable kind of planet. So the transit depth scales as the radius of the planet squared. The RV semi-amplitude scales as planet mass. Bolometric luminosity scales as planet mass to the 2.5. The star-planet contrast in direct imaging for both thermal emission and in reflected light scales as the radius of the planet, basically the area squared, basically as the area. And the astrometric reflex amplitude for astrometry scales as planet mass. And the point here is that for all these methods, mass and radius scale to the power 1 to a few. So it's very sensitive in general. Detectability of planets is sensitive to the size and the mass of the planet. Okay, so in many ways, this is sort of a quilt, and we're going to try to stitch a little bit of this together. So the focus of the giant planets across space and time, so as we move outward in orbital distance, and then a little bit about what we've learned about planets over time, some of their population level behaviors, and the emergence of a story here of how giant planets form and evolve from an observational perspective. And then I'll talk just a little bit about some of what we're doing with respect to the combination of some of these techniques, and in particular using astronomy surveys to image planets. Okay, so what are we learning about demographics? If we consider 5 orders of magnitude over which giant planets have been discovered, the first one's hot Jupiters. We now know that their occurrence rates are very low. So for sun-like stars, 1 out of every 100 might host a hot Jupiter. Warm Jupiters with separations between about 0.1 and 1 AU are a little bit more prevalent, something like 1 or 2%. So the hot Jupiter found around 51 peg. This is now known to be an outlier. But of course, it's driven a lot of conversation and theoretical motivation as to how you get a giant planet a few stellar radii from its host star. The bulk of giant planets have been found between 1 to 10 AU, or rather the production site. So there haven't been that many found actually in this region in comparison to the hot Jupiters, but the prevalence is much higher. So the giant planet radial distribution function peaks in this 1 to 10 AU region with a peak out of 3 AU. As we march, and actually this is one of the more robust features of this distribution. So it's been seen now in multiple surveys. This takes long baselines, decades of careful, patient, continually motivated RV observations with the same facility, ideally, and the same instrument to preserve that baseline without any instrument offsets. But from a combination of HARPS and Coralie and the Anglo-Australian Planet Search and the California Legacy Program, all of these long baseline surveys are seeing a sharp rise in the abundance of giant planets at about 1 AU. And it seems to be preserved several AU, and then in some cases, we're seeing a bit of a fall. So this turnover is beginning to be apparent in these programs. And it's also seen with high contrast imaging. So there have been many direct imaging surveys to look for giant planets at close separations as possible and as high contrast as possible over the past several decades. Most of these have been blind direct imaging surveys. And the beauty of that is you get statistics. You can add it to a plot like this. So they're quite rare at very wide separations, and they're somewhat more prevalent at the 5 to 10% level in the 10 to 100 AU regime. And in general, taking a step back, this picture sort of makes sense when considering the disk surface density and the dramatic rise in the solid and gas densities of protoplanetary disks, which fall by something like 3 orders of magnitude by the time you get out to 30 AU. So most of the stuff, most of the raw materials are located for planet formation are located very close to the host star. And then the ice line is an important process in the formation of giant planets. Beyond this region, when water can condense into ice and facilitate the formation of pebbles and planetesimals, pores, which can then accrete gas to form a giant planet. So this general shape seems to be consistent with this idea of an increasing surface disk density and a demarcation of a water ice line. Now, all of this is in the context of core or pebble-assisted accretion, which is most efficient at within a few tens of AU. At wider separations, cold, massive protoplanetary disks might be able to collapse down and form giant planets following this disk instability route. Beyond that, planets might be formed from cloud fragmentation as the tail end of the binary star formation process. In many star forming regions, when you go all down to the bottom of the eye, the objects in the brown dwarf territory and all the way into the planetary territory down to a couple Jupiter masses have been discovered. So they seem to be the star formation process, and that fragmentation of cloud cores seems to be able to produce objects all the way down to planetary masses. Most stars form in dense natal clusters, and it's possible that in that scenario, dynamical capture could also attach a distant planet at hundreds or even thousands of AU. And these are not theoretical ideas. The most distant planet that I know of is something, or planetary mass object, the scale of 8,000 or so AU. So we're finding these things out there, and these are at least some ideas of how they formed. But when trying to interpret all of this, we're also plagued with this convolution of inward migration through various processes like disk migration at young ages, planet interactions and scattering events over the course of many orders of magnitude in age. And then high eccentricity migration, which is one way to get giant planets. to small separations through three-body interactions. Then there's also an opportunity for planets to move outward. So there are, during these planet interactions, a lower mass object might be flung to the distant regions of that planetary system. And resonant migration is also a possibility. Most of these planets that we've found are at old ages, field ages, something like 3 to 8 gigayears. And so it's very difficult to back out their formation route simply from this alone. And so we have, in my mind, some sense now of where the giant planets are. And of course, there's different levels of detail that we can that we hope to learn about the full structure of this radial distribution function. But in my mind, one of the more interesting questions is how they formed and when they got to these locations. So it's this time axis. So I'm going to highlight a series of results from collaborators and students in my that touches on some of these temporal aspects. And we'll start at older ages, and then we'll move backward in time to younger ages when planets are forming. So I have a graduate student, Marvin Morgan, who's been thinking a lot about the origin of hot and warm Jupiters. Warm Jupiters are especially interesting because they're not tidally circularized by their host stars. So once they're beyond about 10 orbital periods of 10 days or 0.1 AU or so, the tidal influence of the host star is weak enough that we can sort of trust the eccentricities that we detect. So he's reevaluating about 18,000 radial velocities for 200 warm Jupiters, and uniformly fitting their radial their RVs with Keplerian orbits and trends and higher order potential outer companions. And what he's found is that there's a broad distribution of giant planet eccentricities. So this is at old ages. About 3/4 of warm Jupiters have eccentricities beyond 0.1. So as a population, giant planets at these ages are dynamically hot. There's also a distinction with metal-poor and metal-rich systems. So when you look around metal-rich stars, the eccentricities tend to be higher, and around metal-poor stars, they tend to be lower. And so there's a metallicity, host star metallicity dependent distribution function. So he's also been thinking about obliquities. So obliquity is the angle between the spin axis of a host star and the orbital angular momentum vector of a planet. So in this case, the spin axis and that angular momentum vector are aligned, and in this case, they're misaligned. We see this in the solar system. The gas and ice giants are mutually coplanar to within about 1 degree, but the sun is misaligned by about 6 degrees. And this has been an interesting puzzle, and it's not quite clear what the origin of that is. But there's a connection with stellar obliquities to the solar obliquity. Now, there's been a longstanding fundamental result in the field that emerged about 15 years ago and has been strengthened since then, where obliquities of hot Jupiters tend to be higher for high mass stars or hot stars. And this distinction seems to be relatively abrupt, and it coincides with something called, which is a region where that differentiates stars with earlier spectral types and higher effective temperatures. They can't slow down. They don't have the convective envelopes that are required to generate a strong magnetic dynamo that can launch stellar winds and slow the star down over time. So all of these stars have slowed down, and these ones have not. And this coincident alignment of the craft break has been to the distribution of stellar obliquities. And so the general interpretation, the standard interpretation, is that hot Jupiters realign their host stars. So perhaps whatever mechanism produced these hot Jupiters like 51 Peg B initially would have been all over the place here with a large spread in stellar obliquity. But there is a realignment process where the planet can interact with the convective envelope in particular of these stars and realign the stars, so that what we're seeing here at old ages is a dampening of these obliquities. So Marvin measured stellar inclinations for hot and warm Jupiters for systems where this was possible using photometric modulations of the host star coupled with projected equatorial velocities, and found that the underlying distribution of hot and warm Jupiters is basically the same. So this alignment, this relative alignment around cool sun-like stars that are single with no stellar companions seems to be broadly consistent, marching all the way out to about 2 AU. And these are results that have also been found using the RM technique, the Rossiter-McLaughlin method, which is a separate, distinct approach to measure the relative orientation or the projection of that orientation for hot Jupiters and their host stars. So hot and warm Jupiter obliquities around cool stars are similar and generally aligned. And so this reflect a primordial obliquity, which might negate the need for hot Jupiter realignment. Or alternatively, we might just be seeing this as a coincidence where the originally broad distribution of hot Jupiter obliquities dampens over time, and we're catching it at a time when it happens to match that of the warm Jupiters. But one interpretation of this is that hot Jupiter realignment might not be as obvious or evident from the data. Okay. I'm going to move on to work that a former graduate student of mine, Quan Tran, carried out with the Hobby Eberly telescope. So he was interested in when giant planets wander inside the ice line. So at what stage? And if we can pin down the timing of this inward migration, assuming that giant planets form predominantly beyond the ice line, then we can also pin down the mechanism. If it happens before disks disperse, then that would imply that disk migration is bringing these giant planets inward. And if it happens beyond that at older ages, it's probably some other process like planet scattering. So the work was carried out with the Habitable Zone Planet Finder spectrograph at the Hobby Eberly telescope. It was a 45-night program targeting about 100 young stars. So we wanted that age axis to probe that age axis in the 20 to 200 mega-year time frame. These were all sun-like stars, and the goal for this 4-year survey was to march all the way outward to about 4.5 AU. So anyone that's tried to target young stars with radial velocities knows that this is a very challenging effort. So this is some example of the radial velocities that we acquired. And you can get a sense of the scale of the what we call stellar jitter or activity is very high. So in this case, hundreds of meters per second, tens of meters per second. And to show that we could recover a known planet, we also targeted RV standard stars and a couple known giant planets. After the recovery from the survey, a young hot Jupiter orbiting a member of a nearby young moving group with an age of about 120 million years. Its orbital period did not line up with the rotation period, which is one of these tricks that we use to distinguish a real planet from an activity modulated signal. Okay, so counting for sensitivity for each individual star and assembling this into an occurrence rate, we found an occurrence rate of something like 2% with modest uncertainties, which we could compare to the occurrence rate of field objects. So this is old stars with a similar range of separations, 0.1 to 1 AU, 0.1 AU out to 2.5 AU, which is about 6.5%. So this is some of the first evidence that suggests that this occurrence rate might be increasing over time, although we want to be cautious with this interpretation, and it might also be constant. What we can say for sure is that it's not decreasing with a high level of certainty. So there aren't a lot of warm and hot Jupiters that are disappearing over time, at least on these time scales. Okay, so this might be a signature of late inward migration. I'm going to transition outwards and stay at the same kind of ages, a couple tens to hundreds of millions of years, and talk about some of the population level results that have emerged from high contrast imaging surveys. One of the things I've been interested in is eccentricities and spin orbit angles as a probe of planet formation, and especially when comparing them to a comparison sample of higher mass companions at similar spatial scales of tens to hundreds of AU. So brown dwarf companions that have also been found with these methods. In a study from many years ago, we found that the eccentricity distribution of giant planets tends to be more circular, less eccentric than brown dwarf companions. And the conclusion here is that these perhaps represent different populations, different formation channels, with giant planets forming in disks and remaining moderately circular, at least as a population, but brown dwarfs having a much broader eccentricity distribution. And we also found that these long period planets don't have high eccentricities, which rules out, at least as a dominant mechanism, ejection, which would induce high eccentricities. So we can also think about spin orbit alignment by comparing the orbital plane that emerges as we track these giant planets over time, and the inferred stellar inclination, which we can get from measuring a V sin I, a rotation period from photometric modulations, and then backing out the stellar inclination. High resolution spectroscopy gives us, and modeling gives us a V sin I. Light curves can give us the rotation period. And in principle, we can back out a distribution for the stellar inclination. There's some nuance where there's covariance between the projected rotational velocity and the equatorial rotational velocity, but that can be taken into account. So when we do this, we can back out this gallery of posterior inclination constraints on all of these systems with imaged planets and brown dwarfs. And in some cases, they're precisely measured. In other cases, they don't deviate very much from the isotropic prior. So there's little information content from this work for some systems. But for each one, we can compare this orbital plane and this kind of polar plot where we have the orbital plane here mapped out in blue. And there's a degeneracy in the inclination that we infer. And so I call these boomerang plots because they sort of look like boomerangs here. But there's this is basically a posterior distribution mirrored about 90 degrees. And so degeneracy in this inclination. So in this case, for this system 51 Eridani, the system is consistent with alignment and prograde and a prograde orbit. Other systems like Gliese 229, the first T-dwarf discovered and the first brown dwarf companion discovered with observations at Palomar locally. The orbital inclination is very near to the sky plane. The stellar inclination is very close to Polon, and so this has a large projected obliquity. Okay, so this is an example of a misaligned brown dwarf companion. So we can do this with all the systems for which we have this information available. And what we found is that the planets all seem to be broadly aligned. And this is a nice inclination versus inclination plot here that shows the planets with consistent spin orbit alignment. And the brown dwarfs deviate largely from that. So there's much more variance about that one-to-one line. So image planets show a preference for spin orbit alignment. Brown dwarf companions are frequently misaligned. And these point to different formation pathways, organized disks for the planets and fragmenting clouds predominantly for the brown dwarfs. Okay, now altogether, there's more evidence that's mounting here. The planet mass function at wide separations is bottom heavy. Long period planets are more common around high mass stars. So as we crank up the stellar host mass, we're increasing the disk mass, and that produces more giant planets. And the combination of low eccentricities and low stellar obliquities imply that these image planets truly are planets. They're not just the tail end of the binary mass distribution function. Okay, I want to spend a little time here talking about circumplanetary disks. So there's been growing attention to the observational tracers of disks around younger planets. So here we're going earlier in time to the formation, the sites and locations, and some of the properties of giant planets in the process of forming. So there's been a lot of great work predicting what kind of spectrum should emerge during the accretion process of gas infalling from a circumplanetary disk onto the planet, and also what that radiation looks like at longer wavelengths as it's re-radiated. So this is work from Aoyama over the past few years, and Nick here at Caltech in the recent past. So generally speaking, there should be a strong UV excess, of course, line emission from the accretion process and a shock hitting the planetary surface. And then much of this should be re-radiated at longer wavelengths. So we're just starting to see this observationally. We have a few cases of planets, giant planets, embedded within their protoplanetary disks. PDS 70, B, and C are two examples of this. These are giant planets orbiting at a few tens of AU. They've been seen in here. We have the reflected light of its protoplanetary disk with a gap, so it's a transition gap out to several tens of AU. A few years ago, I worked with Yifan Zhou to obtain the first UV observation with HST of this system, and we found from that we're able to model it with an accretion slab model and derive an accretion rate of something like 10 to the minus 8 Jupiter masses per year. So the age of the system is a few, so that implies it's at the tail end of its accretion because it's already a few Jupiter masses. So here's what the data look like here's an HST point here and F656, which is H alpha. So you can see a strong H alpha excess and a strong UV continuum excess. And this was an image that Space Telescope Science Institute put together for the press release. So this is how you might envision it, with perhaps some magnetic field funneling of flows from the disk onto the planet. Now, the same year was the first discovery or first image of a circumplanetary disk at submillimeter wavelengths for a different planet in the same system. So this is a faint detection. It was a challenging detection, but it's the first example of dust being detected from a CPD. So on the heels of this, we proposed for observations with ALMA of a system called SR12C, which is much more distant from its host star and has a mass that's somewhat higher, 11 Jupiter masses. But we knew it's accreting this extraordinarily strong H alpha here. And here's kind of the typical spectrum of a young early L dwarf. So we proposed for HST and JWST and ALMA and recovered the companion in wavelength spanning 0.2 microns all the way out to 880 microns. So this allowed us to start to build an SED of this system and fit it with accretion models at short wavelengths, and in this case, a 2-temperature black body at longer wavelengths. And altogether, this gives us the first glimpse of a multi-wavelength SED for a forming planet. The inferred accretion rate is 10 to the minus 11 solar masses per year, which is similar to PDS 70. That's 10 to the minus 8 Jupiter masses per year. So over the course of 1 million years, it should only gain 0.01 Jupiter masses in mass. And the inferred radius is at the scale of 1,000 or 2,000 Jupiter radii. So this is the first of growing sample. We have other examples. This is a larger program for, I think, 8 objects altogether. So we have JWST Myrs observation sampling the disk properties up to 20 microns, and HST data going all the way out to 0.2 microns. Now, another aspect of this that's quite interesting is the ability to probe the 10-micron silicate dust feature. So these are grains, silicate grains that are inherited from the ISM. They're incorporated into protoplanetary disks, and they're common sites or commonly observed as emission features. When grains start to grow, these signatures start to fade away until they become undetectable. So in some cases, like FU tau B here, we see a strong spike at 10 microns. That's an indication that those grains have not yet coalesced and grown and settled into the midplane. But in a few other cases, like SR12C, that clearly has been the case here. So sample some of the diversity of these initial conditions of the formation, giant planets, and of growth of solids within their disk. Now we can compare this to the submillimeter fluxes to trends that have emerged in the submillimeter regime of other disks, and it seems to follow, at least for PDS-70C and SR12C, a huge sample of 2. We can say that both are compact and both are consistent with extrapolation from circumstellar disks, and we have many non-detections here as well. For the sake of time, I'm going to go ahead and jump forward to the last part of the talk, which is the orbits and masses of giant planets with astrometry and direct imaging. So this is a new, I mentioned earlier that some of the most exciting results in terms of statistics and early discoveries from direct imaging focused on blind direct imaging surveys with no other evidence of there being a planet there. And with that, we get good occurrence rates. And we're in an era now, and one of the trends that have emerged is to basically ditch all of that and look for clues of where giant planets are so that we can image them, measure their orbits, sample their atmospheres, study their atmospheres, and move the field forward, because we've been a little bit plagued in the field with a lack of discoveries, at least in comparison to planets at smaller separations. So one way to do this is with Hipparcos and Gaia. So Hipparcos was a mission that flew in an astrometric mission that flew in the early 90s. Gaia, of course, is, well, it's now no longer observing as of earlier this year, but the data are still being processed and releases are still happening. So we can use proper motion anomalies or astrometric accelerations. There are a few groups that have done this. One is led by Tim Brandt and another Pierre Curvella in Europe. And we're limited here by the size of Hipparcos, which is about 110,000 bright stars. But when cross-matched with Gaia, about 30,000 accelerations emerge, significant accelerations. Of course, most of those are binary systems, right? Any binary is going to produce a strong astrometric acceleration if it's at the right orbital distance of a few AU out to tens or even hundreds of AU. But the sensitivity is such that giant planets can be detected this way. So for a given acceleration, there's a couple implied degenerate masses and separations. So this is planet mass and separation for a particular system. At wide separations, there's a power law relationship that connects for a given measurement the implied mass and separation. At the scale of the baseline of Hipparcos and Gaia, there's a turnover, and then there's aliasing features at shorter periods. But we can use this and apply it to the entire sample to identify systems that are definitely stars, in which case we don't want to observe them, those that could be brown dwarfs at modest separations, and those that might be planets. So I've been carrying out a survey with my former student, Kyle Franson, to do just that. And there are other groups that have done this as well. And this is just a gallery of some of the discoveries. And I've listed, one of the nice things about this is we're seeing the reflex motion of the host star. And when you do that, you can directly measure the mass of the companion that's inducing that reflex motion. So you can see the scale here of the masses. So at the scale of tens of Jupiter masses, these are the brown dwarfs. And then a couple planets have been found this way. One of the most exciting systems is AF-LEP. This is a companion that was discovered with Keck and also Sphere by two other groups independently. It has a contrast of 10 magnitudes in L band. It's located in AU. It's a young system. It's in one of these nearby young moving groups, which has an age of 24 million years. And there's a debris disk located farther out. This is a disk of dust that hasn't been resolved yet, but the inferred like 50 AU. The orbital inclination aligns with the stellar inclination, and it has a dynamical mass of about 3.5 Jupiter masses. So that makes it the lowest mass directly imaged planet with a dynamical mass and one of the lowest mass imaged planets. This plot shows mass versus separation, all of the imaged brown dwarf companions, the imaged planets, and then those with stars are those which have direct mass measurement. So one of the exciting things about this is it allows us to test atmospheric models and evolutionary models. It's been observed now with JWST, basically every instrument that's been able to target it. And I think it's been the most characterized or the fastest characterized image planet with basically every suite of instruments that was just ready for this kind of planet, observing it over the past few years. I also see it as being the precursor for what we're going to be able to do with Gaia. So I'll just spend another minute or two here talking about the landscape in the near future of giant planet demographics with the upcoming data release of Gaia. So for those of you who are unacquainted with the various data releases, we're in data release 3 right now. These are proper motion and parallax fits to almost 2 billion stars. There are also radial velocities and a whole suite of other information that's been delivered to the community. The 4th data release is coming up in December 2026, so just over a year from now. And this will include epoch astrometry, so all of the individual measurements and uncertainties will emerge with this. And it's exciting because that's where we think the planets are gonna be. Based on the expected sensitivities, the number of planets is going to be at the scale of 10 to the 4. Certainly several thousand, if we're lucky, maybe 10,000 for this 4th data release. There is also going to be a 10-year baseline data release in probably 2030, maybe beyond that. And that will double the baseline of DR4. The expectation value is about an order of magnitude larger than that. These are for closed orbits. So where we see the full orbit, there will probably be many more accelerations, longer period accelerations. One of the nice things about astrometry, this is a whole new method in our field. We have basically among the 6,000 planets, almost none that have been found with astrometry. It depends on how you're counting. But we're about to enter a new era that will be, at least for giant planets, at modest separations of 1 to 7 AU dominated by astrometry. It's insensitive or relatively insensitive to stellar age, which means that we'll be able to probe this time domain. So we can study eccentricities or stellar obliquities over time from 10 million years to 100, 1 gig a year and beyond. Planets can't hide from astrometry. So with direct imaging, they can hide under the contrast curve. With radial velocities, if you have a face-on orbit, you get no reflex motion in the radial direction. But with astrometry, regardless of the orientation, you either get back and forth motion for an edge-on orbit or circular or eccentric motion in the plane of the sky. So as long as you reach the sensitivity to find the planet, it will reveal itself if you understand the systematics and all the other nuances associated with the data. So I'm especially excited about this new era where orbits, masses, inclinations, and demographics will be available for thousands of planets as a function of all the parameters that you can imagine are important to the planet formation process, like age and metallicity and stellar mass and separation, stellar metallicity, planet metallicity, et cetera. Okay, so looking ahead, DR4 is going to be an exciting new era. It's going to require a lot of vetting, both with radial velocities and imaging. In the DR3 version of the planet candidates that has been released, there's sort of an uncomfortably large fraction of false positives that should be much lower in DR4. But regardless, there will be thousands of planets. It does require heavy lifting from the community, though. Upgrades to existing instruments and new instrumentation at facilities like Keck with scales and high spec, and upgrades to GPI, MagAO, Sphere, et cetera, I expect will be relevant for this DR4 era. We're going to be able to image the planets, measure rotational broadening, and also start to think about their rotational evolution. And finally, JWST and the ELTs. We're already in this era for JWST. The sensitivities that are emerging for direct imaging allow us to probe mature planets for the first time at wide separations, and also get us down to sub-Saturn masses at tens of AU. Okay, I'm a little over, so I'm just going to end there, and happy to take questions. Thanks. Yeah, so everything we've assumed here, this kind of analysis is assuming one planet. Two planets, which are probably prevalent, and and there seems to be correlations among smaller planets of peas in the pod and comparable architectures. If that's the case for giant planets, then certainly that can mess up the acceleration. This has been seen in a couple systems. So one of the first examples, or maybe even the first example of a planet that's been imaged based on its anomalous astrometric acceleration, had an anomalous, when there's a known outer low mass brown dwarf, and when the acceleration was incorporated, there's a residual that was very strong, and that hinted that there was another planet, and it was found with an instrument called gravity. So it can certainly mess it up, and can also bias things like the orbit fits if only one planet is assumed. Yeah. Yeah, so metallicity and stellar host mass are two of the strongest parameters that giant planet occurrence rate scales with. In this case, these are young moving group members, and they have kind of comparable ages to, or comparable metallicities to the field population for the Johnson et al. Work. In that case, so we didn't make any corrections in that case, and we also made sure to isolate the stellar host mass range to be similar. So from our view, it was sort of the first, or maybe the second. There have been a couple examples of these attempt to assess that age dependence. And again, the constraints are weak, so I don't want to oversell it. And it is consistent with a constant occurrence rate. But the preferred solution is sort of a trend upward slowly. Yeah. One of the things my former student's going to do is amass all of these together, and the goal is to pin down those uncertainties better. Yeah. Yeah. Yeah, so the interstellar asteroids or comets are certainly connected to the existence of giant planets. That's the inference, is that they are remnants in the same way Jupiter scattered most of the planetesimals in the early solar system. I suspect that it will be very challenging to back out something concrete about the prevalence of planets or anything specific like that. Certainly in the sense of compositions, I think that would be very interesting if, for instance, there are trends that are mimicked in the solar system with asteroids and sort of gradation of compositions moving outward in the disk. I think that will point to where the things emerged, but I think it will be hard to connect that to something more specific than that. I mean, there are ideas to go visit some of these and sample them, which are crazy now, but perhaps not impossible one day. They're clearly everywhere, though. The inferred space densities are very high. Yeah.
The around our
12.
or evidence of a potential gearing in the disk, from the here.
Or like a moon or something, yeah, that dynamically cleared it. So that was the first thing that we were looking for, and just the simplest Occam's razor kind of fit. We fit it with more complex models, but the double black body, might reveal something like that. To be perfectly honest, coarse spectral sampling with photometry with Myrs out to 20 microns, unless there was a very large cavity and you would see a steep decrement. That's not going to be evident. It's possible at shorter wavelengths that might be possible, but yeah, we didn't see any sign of it is the answer. Yeah. We're on the lookout for that though. Yeah. Good question. I think we just took evolutionary models. So 2 million years, the bolometric. Oh yeah, I think it didn't change things by a ton either way. If you're assuming boundary layer right up against the surface of the object, or a couple stellar radii away, it changes it by factors of a few. But I don't believe the numbers anyway. So I'm giving you what the math says, But there are so many nuances in inferring true accretion rates. I don't think, certainly in the planetary regime and even in the stellar regime, it's very challenging to go from H alpha or even the UV continuum to something concrete. So I wouldn't trust these to better than an order of magnitude. And that's probably, yeah, probably less precise. Go ahead. Sorry. Thank you. The outside in is just the observational strategy. So with direct imaging, moving from the outside in, yeah. So not physical, yeah, not evolution of the disk or anything like that. Yeah, in fact, there's the opposite from timescales of disk evolution, that it seems to be an inside-out clearing process. Yeah. Proto-moon, so so that's the direction where we want to head. So, being able to study these circumplanetary disks, their accretion rates, connections to the disk sizes and masses and radii and physical properties. Presumably there's a trend, or this is what we want to look for, is a trend of disk properties over time, accretion properties over time, and see if they track together. And if so, how do they track? There's something that's I've been really interested in with respect to disk dispersal timescales. So for protoplanetary disks, the disk dispersal is connected to photoevaporation and MHD disk winds, and viscous accretion and planet formation. Those are kind of the things that can clear a disk. For when you're in the planetary regime, you've removed much of the XUV radiation that can produce photoevaporation in those winds. And so you're left with accretion or moon formation. And so I wonder, and it's just not been measured yet, this is something I'm interested in, is that time scale that we quote in the community of 5 to 10 million years for the disk dispersal for protoplanetary disks. Is it similar or distinct for planets? And there's many aspects of this, of planets being replenished within a circumstellar disk or far out that's just left to its own, to viscously evolve. But all of this is unconstrained right now. So I think these are directions we want to go in. Yeah.
You've been able to say quite a lot about how they can write the accretion, the addition outside. I mean, everything seems to make it.
Yeah.
But also possibility of atmosphere.
That's right.
Crystallize
Yeah.
quite nicely. So for you, right? We've been able to do that with data. Now we're going to get, orders of magnitude more data and sensor values, right? So what excites you more? What questions are you seeking to address?
Yeah, great softball question. So Gaia is going to be a revolution, and no one here is really ready for it. We talk about it, and we get some preliminary data, and we can get it for a couple DR3 deposited planets that have been given to the community. But I think nobody's ready for the onslaught of planets and then issues surrounding the data set as well. And there will be systematics that are unexplored. There will be biases, eccentricity biases, probably inclination biases, lots to unpack and divide through the results if we want to get demographics. So I'm interested in that. I'm interested in whether we'll learn something about when giant planets interact to take on the eccentricities that we see at older ages. I'm interested in structure in all of these distribution functions. So just like the radius gap that separates small, compact, rocky planets from those like Neptune-sized planets and sub-Neptunes that seem to dominate in a bimodal sense the small planet population. That was only uncovered when there was better precision by a factor of a few for all of the host stars, and then that propagated through to the radii of the planets. And so with all of these new planets that are going to emerge, I'm very interested in that radial distribution function. If there'll be structure in there, if we see, maybe an enhancement at the kind of characteristic snow lines, if there's structure in the mass function or the eccentricity distribution. And I've been trying to encourage theorists to give us some predictions. You have like 13 months to do it. But give us predictions on what we might look for and also help motivate the follow-up observational efforts. Because we can go and measure things, but then interpreting it really requires a fundamental, physical and theoretical kind of foundation. And it'd be nice if there were predictions to motivate a lot of this work that we are all going to do kind of regardless. But let's connect it back to the science and the physics. Yeah. Hey.
I have a question.
Yeah.
Which I didn't have.
Sure.
So the DR4 candidates, they're like filled with false positives.
The DR3 ones
Like,
are,
yeah,
yeah,
full of
yeah,
false
that's right,
positives.
yeah.
But what I haven't heard about is the false positive rate on the Hipparcos Gaia ones.
Yeah,
I don't
yeah.
actually think there have been very many false positives.
Well, there have because, and they're not published. So like
Okay.
false positives meaning like a stellar companion
that's what
at,
I mean.
100 AU
Right.
everywhere. So something like a third of the targets that show interesting accelerations have like a low mass M dwarf at, 100 AU.
Okay.
They're going to be published. There's like, I'm forcing Kyle to publish this big survey with,
Okay.
1,000
All right.
AO and speckle images. And so those will come out. It's just hard because there's so much weird human selection function that went into like,
Huge selection.
yeah, but that, if we want to call that a false positive, it's very high. Yeah. Third. Yeah.
Oh, okay. But
Yeah.